Hey again, everyone. Welcome to Lecture 13 of Environmental Sciences 347 Climatology. In this lecture, we're going to briefly look at the climate classifications, what's the nomenclature of certain climates globally, and then look at how we respond to climate change, a planet that is warming a little more rapidly, actually a lot more rapidly than it would naturally. So first off, let's go back and define what some of the classical classifications, if you will, of climates. What are the names that we give to certain climates? These go back to Vladimir Koppen, who developed this classification in the 19th century to early 20th century. He's a German climatologist and botanist because you've got to look at what's going on in the biosphere to come up with some idea of what kind of vegetation, flora, fauna that the climate will support. And of course, revisions are always being made. And it's important to realize that because the planet is round, we've got mountains, we've got rivers, we've got lakes. No one size fits all, but this gives you a general idea of some of the climates globally. The tropical humid climates, these are exactly what you think they are. They are muggy, they are humid, they exist in the tropics. All right, these are places that there's just not that much variability throughout the year. Sometimes they're wet, sometimes they fluctuate between wet and dry, but they're almost always humid, and there's just not that much temperature change throughout the course of the year. This is the kind of stuff we see near the equator, tropical rainforests, that kind of stuff. Dry climates, by definition, of course, you think arid, you think about a desert. These are places in the world where the average rainfall for the year, all right, doesn't really meet the needs, if you will, of what's out there. So the average annual precipitation exceeds, the evaporation exceeds annual precipitation. So there's more evaporating out than is coming back in versus precipitation. Right? That's kind of how we define what a dry, what an arid climate is. There's more evaporation, more water going out than is coming in. And this comes on several secondary levels, depending on what kind of temperature you've got going on. Again, dry is one thing. I mean, technically, Antarctica is a desert. It's an incredibly cold desert, but it's a desert. But you can look at things that are warm and dry, cool and dry. They're a little bit arid, or they're fundamentally a desert with very little precipitation at all during the course of a year. Subtropical climates, these are ones that you begin to think of places like the southeastern United States. You begin to think of places like San Francisco, California. Some places are a little drier than others regarding total amount of precipitation. And those are Mediterranean type climates. They are dry during the summer, will tend to be wetter during the winter. But there are other ones that are subtropical, dry winters, which we kind of see in the southeast. It certainly rains there, but we tend to have more rainfall during the summer versus the winter. So Hong Kong, San Francisco, these subtropical. They're not cold, but they're certainly not tropical. They're closer to the tropics. So they do run a large range of temperature from warm, cool, and cold. The snow forest, these are places that get precipitation all year long. And of course, during the dead of winter, it is cold. It is powerfully cold. Yellowknife, Canada is in the Northwest Territories there, far northern reaches of Canada. They have very, very mild summers, all right, but bitterly cold winters as a general rule of thumb. They get precipitation all year long. And again, these things come in different flavors, from cool winters, warm summers, to just ridiculously cold winters and still some cold summers. But, you're getting year-round precipitation and it's forested. And each one of these comes in a different subcategory. Finally, we're going to do a couple of these special ones like polar climates. You've heard of tundras, and then what legit ice caps. Ice caps are places that are iced over all year, whereas tundra tends to be flat, has very, very sparse vegetation, but it does have a tiny bit of vegetation. whereas an ice cap really doesn't. Very high mountainous climates are just known as highland climates. This is where the windward sides are going to have more precipitation than the leeward sides. You think about any mountain that is sitting up a couple thousand feet above the valley below, and as the winds run up against that mountain from, let's say, from the west, that's going to squeeze out precipitation and cloud cover as those winds go up the slopes. As we talked about earlier on in the course, that same wind comes down the other side, and it is drier. So these are highland climates. Another very good example for this is Mount Washington, New Hampshire, and to a lesser extent in Virginia. We think about Hot Springs, Virginia. Not so much there at the Homestead Resort, but going farther northward up along the ridgetop locations. That's a different type of climate entirely. So then we start thinking about how do we respond to climate change. In other words, what are we going to do about this situation to slow down a climate that is warming way faster than it's ever done in the past, naturally, because of the things that, quite frankly, we're doing as humans to generate energy and live our lives. So, a lot of energy is still used is used from fossil fuels. That's where we still get it. What we have seen in the past decade is peak coal. Coal isn't dead, but it's gotten as big as it's going to get. All right, and there's a lot of chatter about, well, renewables are taking away coal. That's not the case. Renewables are very slow to grow until the last few years, where they've begun to accelerate dramatically. But what is killing coal is natural gas. The fracking industry, hydraulic drilling is what's really killing coal. So that's why you see the gas there in blue jumping. Oil continues a methodical but slower increase, and coal has peaked and is probably starting to go down. So there's still way too much fossil fuel being burned, and that's still a problem. And while it is true that China has surpassed the United States in the amount of carbon dioxide emitted annually, when you think of it per capita, the U.S. still runs circles around China. Of course, China has a massive population, over 1 billion people, compared to the United States, just because we have a higher standard of living. Fair or not, that's just the way it is. So when we look at how much fossil fuel use per capita, specifically to carbon dioxide emissions, USA is still easily on top, and distant second is Russia, then Japan. Again, Japan is a very highly industrialized economy, and then you start dropping back to things like China and the EU, and then globally. And India is on the way up, and you've got to remember they've got a massive population in excess of 1 billion people. So the idea to kind of slow down a warming climate in its tracks is these places that have developing economies to basically shortcut them right into renewable energy. You don't want to introduce fossil fuels, because then you're going to have to take them out. So as these countries start to develop more, and they have more mature economies that require more energy, you want them to go directly to renewables wherever possible. When you think about how much carbon is going into the atmosphere, how much carbon is going out of the atmosphere on any given year, all right, there's a big interchange going on. We know there's massive amounts of vegetation. There's massive oceans. All right, those are where a lot of the carbon is exchanged. All right, so you've got vegetation and a net production and respiration. You've got oceans outgassing and absorbing. So there's a lot of those two things going back and forth. The problem is, when you look at how these play out, fossil fuels, and to a much lesser extent, cement emissions, because that's a greenhouse gas emission, and changes in land use. When you add those to this total carbon budget, you still get a net addition to the atmosphere of about 2 gigatons a year. That's just in North America. All right, so A lot of what we see in terms of carbon dioxide we're putting into the atmosphere from human activities, about half of that is actually going into the ocean. Right? So we're like, well, we're putting all this CO2 in the atmosphere, but we can't seem to account for it to the atmosphere. About half of it is actually going into the oceans. That's doing two things. It's warming the oceans, and it's acidifying the oceans, which we talked about before, changing the fundamental pH of the oceans. And that's why we see things like coral reefs bleaching. We're starting to see other mollusks and shells being harder to build by oceanic organisms because the ocean isn't turning into battery acid, but it is starting to turn gradually more acidic. Three basic topics as we look more closely at what to do about the situation. There's mitigation, adaptation, and geoengineering. Those are the big three key elements. We'll start with mitigation. That's just reducing the severity of something. All right, adaptation is dealing with it as it arrives. What can we do to better deal with it, or better adapt to what's going on? So we're trying to reduce the severity, and then once it does happen, how do we deal with it? And then there's this other thing called geoengineering, which I'll tell you what, I'm just not a big fan of this at all. I'll be upfront about it. I'm not going to fib to you. They are big, risky global experiments. And I think while it's important to do investigation about geoengineering, most scientists, most geoscientists will tell you that geoengineering is generally a bad idea. One, because of unexpected consequences, and two, for geopolitical reasons, how would you ever pull some of this stuff off? Who decides how to do what? But anyway, let's put the cart before the horse. All right, mitigation. All right, when we look at the lifetime of a gas, the time it takes for a perturbation or a change in the gas to be reduced to about 33%, 35, 36, 37% of its original amount. The idea here being is that carbon dioxide, once it goes in the atmosphere, stays a very long time. Other gases stay up for a long time. Methane does not, but carbon dioxide, nitrous oxides tend to stay up in the atmosphere for a very long time. When we think about what are we going to do about carbon specifically, you've heard of cap and trade. These are quotas or caps imposed on a CO2 source. All right, and let's say you're allowed X amount of CO2, and you're allowed to send out X amount of CO2, and you're allowed to send out X amount of CO2. You could kind of buy rights from other organizations to emit more CO2 if they emit less. So you know what? I get some serious manufacturing over here. All right. I know you guys over there don't use as much CO2. All right, but we're both entitled, if you will, quotas, if you will, to let's just say a ton. All right. Well, I really need to send out a ton and a half. All right. I can buy your carbon rights from you for a fee, and then these people get more money, and then they are going to put out less CO2. So that's the general idea of what cap and trade is between businesses, whether it's across the state, across the country, or across the globe. An offset exchange is when you have carbon credits earned for investments in projects that will offset emissions. In other words, hey, I did this cool thing in my country or in my state that's going to reduce CO2 emissions. Oh, great. Well, then we'll give you a few additional credits so that can continue. Or you just straight up put on a tax, a fee or a tax on carbon dioxide emissions. And then that can fold back into the whole cap and trade thing. So there's a lot of interesting economics that go on with all that. I'm not going to delve into that, but so much since we're not doing economics in this course. But alternative energy, renewable energy, and some of these places it's renewable energy, nuclear, not so much. But solar, wind, hydro, geothermal, tidal power, which is, it's out there, but it's not a big thing. And of course, nuclear. You've probably heard of CCS, carbon capture and storage, where you burn the coal, or you could do oil as well. Heat converts the water to high pressure steam, drives a turbine that makes the energy, and then basically you have some scrubber or something on your smokestack that captures the CO2 going out, goes through another system, effectively liquefies it, and drills it deep into the ground, way down below the bedrock, deep into the ground, so it just stays down there. So that's the whole idea of capturing it and you're storing it in a subterranean way, CCS. The other thing is really improving the transportation sector efficiency. All right, that's a pretty big, it's almost a quarter of energy-related emissions of CO2 come from moving people and stuff around, whether it's you, me, trucks, whatever. All right. So what we need to do, and I think what you'll see nowadays, most professionals in this space are suggesting we electrify transportation, whether that's an individual's car, truck, whatever. Or the other thing is rail transport, electrified rail transport, whether that means goods and services or people from one city to the next. The one good thing that's starting to come around is that these batteries, in terms of individual automobiles, you've heard of Tesla. All right, these are getting better. That can extend the range and efficiency of electric vehicles. Last I checked, and it's been about a year, I'll be honest here, your Teslas can go about 300 miles on the charge. And some of the superchargers can charge your car in half an hour and go another 300 miles. So it's not quite as fast as filling up at a gas station. But as the charging network starts to scale up nationwide, it's going to become easier and less of a hassle, if you will, to own an electric vehicle. We also think about architecture, consider your indoor comfort, and how that relates to your building infrastructure. How are you going to make a building that uses less energy? Deciding on where you're going to put the windows, the area around it regarding landscaping. You don't want pavement all around your building. You want good ventilation to keep the temperature in your building the way you want it. The color, the roof, the walls, those things are important too. We talked about, things that are black and the visible, they absorb energy. Right? So all those things need to be considered in architecture. With that in mind, you might hear this term, and it's good to be familiar with it, something called a heating degree day or a cooling degree day. And these are weird because these really aren't days at all. It's just an odd name that's developed over time. It's an indication of what an average daily temperature is. For example, engineers are trying to decide how much they should plan to heat or cool a building throughout the course of the year. So if your average temperature is below 65 degrees, it's a heating degree day. So in other words, if your average temperature is 64 degrees, that's one heating degree day. If your average temperature is 60 degrees on that day, it's 5 heating degree days. It's a very weird nomenclature. It does work the other way around. Let's say your average temperature for the day was 75. That means you had 10 cooling degree days on that day. I don't know who came up with this nomenclature, because I like to have a few words with them, but it is what it is, and this is just the way it's stuck. So we already have seen warming of about 1.5 degrees to 2 degrees Fahrenheit over the last 100 to 120 years, nationwide, globally. All right. So we can mitigate to slow it down, but then we have to adapt to more warming and the impacts of that warming as it happens. So that comes under adaptation. One of the things that's probably most important about adaptation is coastlines. We've got to think about what are you going to do as the water levels come up. The other thing you need to think about in urban areas is how you're going to modify your infrastructure. And you're going to have heavier rainfall. You've got to think about more effective drainage system, flood control. Are there going to be new traffic patterns? You're going to have people moving away from the coast, not all at once, but over time, let's say over 20 or 30 years. As coastal flooding initially becomes more frequent and people decide, well, I just don't want to live here anymore. These are the kinds of things we need to think about regarding adaptation, infrastructure, road beds, drainage system, coastal management. All those things fall under climate adaptation. There's one example is Bangladesh, which is an exceedingly low-lying country. A lot of estimates right now in terms of global sea level rise are anywhere between a foot or two to 6, maybe even 7 feet by 2100. So not just do things get flooded, but places that may not flood have their water tables come up below ground, subterranean, so that your salinity levels come up so that you can't grow stuff there anymore. All right. So your salinity levels come up, you can't grow things. There's massive crop failure, and there's a bunch of people that live there. So people are going to be in a lot of trouble regarding food security, and they might just move. And where are they going to go to? Are the people in India going to take them in? In Burma? Ugh, that's a bad scene. Or up in Nepal, where, oh my heavens, Nepal, so you're going from sea level in Bangladesh to Nepal, which is the Himalayas, for crying out loud. So you've got some big changes happening. And you think about this, well, that's way on the other side of the world. And that's true. But sometimes you'll hear the term climate change is a national security issue. What happens if it destabilizes this part of the world and you start to have more social unrest, upheaval, government struggling, collapsing, that kind of mess? That's why we talk about it as a national security issue. Geoengineering is exactly what the term suggests. We're re-engineering Earth. And this is one of these things that it's important to study it, to try to understand what kind of limitations we're under. Specifically, this means a large-scale and deliberate manipulation of the climate system, deliberately manipulating the climate system for the purpose of reducing substantially the anthropogenic contribution to global climate change. In other words, reducing the amount of solar energy coming into Earth, all right, and increasing the amount of heat escaping to Earth by reducing the amount of CO2 in the atmosphere. Now, neither one of these is easy. I would argue if you could find a way to tactfully and controllably remove CO2 from the atmosphere, that's probably better. And I don't really think that's geoengineering as much, because you're not fundamentally changing the Earth system as much as you would in some of these other instances. So some of these sound rather benign. You can replant tropical forests in a low-cost way to remove carbon dioxide from the atmosphere. That's great. But when you do the math, it's just not enough to pull carbon out of the atmosphere to the rate that we're already putting in. All right. And that also has the potential for environmental disruption in places where there are developing economies. So, planting trees is always a good idea, but you can't plant enough trees to fix it, so to speak. There's also this idea that you can just put a bunch of crud in the atmosphere. And by that I mean sulfurous haze, mimicking volcanic eruptions by releasing sulfurous aerosols into the atmosphere. You would have to put up millions of tons of sulfur dioxide every year. All right. This blocks sunlight when the sun is out, so you're decreasing the amount of incoming solar. But you really haven't changed the outgoing terrestrial infrared radiation, all right? But you are cooling the planet from the top, from the sun coming in. So you can have a lot of bizarre, unexpected consequences by doing that. You could also increase the reflectivity of ocean clouds, but this would take something to happen on a massive scale, trying to spray microscopic seawater drops into the atmosphere from ships at sea, making the clouds a little brighter, maybe, but that the scale of something like that is going to be just phenomenal. And now you're starting to tinker with regional temperature patterns and then regional atmospheric circulations, sea breeze circulations, those kinds of things. So that's another system you may not want to be messing with. So the end result with geoengineering, it sounds like a quick fix. It's a complicated fix. And we say quick, I mean, not really quick because it takes a massive amount of engineering. But it changes the risk amongst nations. And this is also just a geopolitical nightmare. Who's going to say what's right for everybody? Because frankly, Russia stands to gain a lot from a warming planet. They would love to have all that Arctic coastline open up. It's really good for their business. So geoengineering probably isn't going to fly. It's important to look at these things scientifically and study them, but these are not solutions that are going to fly. All right, quick lecture tonight. So what I think you all need to do to kind of take all of this in. I put this link on Moodle at the beginning of the course, and this is the time, if you have not watched this documentary, go do it this week. This is from Penn State geoscientist Professor Richard Alley. It's called Earth, the Operator's Manual. And it kind of covers how we know what we know, all in terms of how we know the planet's warming, and then how to attack this idea of energy use going forward to basically mitigate what's going on. Not a whole lot about adaptation or geoengineering, but those other first 2 points. So the link to this is on Moodle. You can watch it on YouTube. It's about 50 minutes long. So break it up into a couple parts if you want. Pop you some popcorn, or have some pizza, whatever. It's good. Richard Alley's really smart. He goes to glaciers himself and talks about glaciers. He goes into peat bogs to show you how fossil fuels form. It's good. It's good. So make it a point to go watch this sometime this week. And with that, we'll end it there for this time. And that only leaves us with one lecture left before we kind of sum things up for the course. We'll talk a little bit about climate change policy. I'm not going to get into like the political issues with it, but we will talk a little bit about why some things are harder to accomplish than others. So with that, thanks so much. We'll talk to you next time.